This set of notes deals with some odds and ends. First of all, how to use Tanabe-Sugano diagrams for tetrahedral complexes, and also where do the brightest colors, the most intense absorptions, come from in metal complexes. So far, the use of Tanabe-Sugano diagrams has been restricted to octahedral complexes. That's typically how these things are designed and posted. But it's possible to also use these for tetrahedral complexes. And so we're going to just look at one example here of what happens if we have a D1 electron configuration, right? So in an octahedral complex, of course, the one electron is in the lower lying T2G orbital. And for tetrahedral complexes, it lies in what's called the E orbital instead, right? Now, the way that these split in terms is not too hard to understand. So you could say that this single electron in this T2G orbital has 3 possible positions. It's triply degenerate. And this multiplicity would be a doublet because we have a single electron. The spin, capital M sub s, is 1/2, right? So this would be correlated with the term s. And so 2s plus 1 gives us the multiplicity, which would be a doublet, okay? Where you could say that there's just simply 2 ways that this electron could be oriented, up or down, right? So it's a doublet T ground state. For the tetrahedral case, it's a doublet E for basically the same logic, except that now we have a doubly degenerate term. We could have this electron in either of these 2 positions. If you go through the full derivation to figure out the group theory of this thing, that you'll find that it's in this E, doubly degenerate representation. Okay, and it's also a doublet for the same reason as we had before, a single unpaired electron. So a doublet E is the ground state there. So we need to define those because we're going to now compare what happens if we look at a different configuration, right? So here's a D9 configuration. And so let's just take a look at what our terms will be for each of these cases. So we again have an octahedral example, and now everything is filled except for one space right here in this EG orbital, right? This would be the last electron to fill. And so the question is, what's the term and what's the multiplicity? Well, like before, we have basically 2 positions for this empty space. We could call this a hole, right? It could be over here or over here for the spin down electron, and then there would be other ones for the spin up electrons. All of those together comprise a doublet E ground state, really for the same reason we had for the tetrahedral case below. So for the tetrahedral example down here, we have a hole, a space in this T2 orbital, right? It's not room grounded, it's just T2. And that can occupy any of these 3 different orbitals. So again, it's triply degenerate, and it's a doublet because this space here could either be the spin down missing or the spin up, okay? Doublet T state, okay? So what's interesting is that we see this doublet T here show up in each of these configurations, but one of them is octahedral and the other is tetrahedral, right? So there's a link between these sets of configurations, right? The tetrahedral, oh, that's not what I want to do. Sorry. Yeah, highlight. The tetrahedral case down here is correlated with the octahedral case over here. So D1 tetrahedral is correlated to a D9 octahedral case, and likewise, the D9 tetrahedron is correlated to the D1 octahedron. And so let's summarize what that means overall. So to understand a tetrahedral complex, what we saw was that the ground state of a D1 octahedral complex is identical to that of a D9 tetrahedral complex. We're just talking about the term, the ground state term, okay? And this is now a symmetry term since it's in this distorted shape. It's not a free ion. So D1 is correlated to D9, and so what's generally true is that if you use the Tanabe-Sugano diagram for D10 minus n for any n electrons in a tetrahedron, right, in a tetrahedral complex, you'll be using the proper diagram, right? So D1 is associated with the D9 octahedral diagram. If we had, for example, a D4 tetrahedral complex, we would use the D10 minus 4, we would use the D6 Tanabe-Sugano diagram, right? And that's all we need to do, okay? We won't work a separate example right here, because other than that, it's exactly the same process. We don't have to worry anymore about the original shape. We just pay attention to the diagram that we need to use, and we solve it using the same kinds of transitions we would have used for the octahedral complex. So the last topic to talk about right now is the kinds of transitions that are typically forbidden. So what we said with our selection rules was that there's a multiplicity selection rule, or spin selection rule, that says we have to maintain the same multiplicity in the ground and excited states, and we're going to assume that that's followed. There's also this Laporte selection rule, which states that you have to have a change of the symmetry with respect to inversion. So that means you can go from a Garada symmetric with respect to inversion to an Ungarada, or vice versa, right? So this means that D to P, for example, would be allowed, right? But you cannot maintain the same symmetry with respect to inversion. So D to D transitions are forbidden, right? And likewise, like D to S, those are both Garada orbitals. They're both symmetric with respect to inversion. Those are forbidden. We can go from a D to a P, or from a P to an S, or something like that. That's okay. And of course, in molecular orbitals, there really aren't any isolated D or P orbitals or anything like that at all. They're all molecular orbitals, but they do have this kind of symmetry. So since those transitions are forbidden, all of these transitions we've been talking about, these D to D transitions going from T2G to EG and all these things, they're all forbidden. They're all going to be very weak. But there are definitely metal complexes that are very strongly absorbing, used as dyes. And those are somehow following this Laporte selection rule, right? They're somehow allowing these transitions to occur, and they're not D to D transitions. So let's take a look at the two different types, okay? So one of them is called ligand to metal charge transfer, okay? And so we have to think about what that means. There really aren't any electrons only on the ligand and only on the metal, because everything is mixed together, right? But if we look at our sort of simplified MO diagram, you know, over here was our ligand electrons. And they came, in this case, we're assuming this is octahedral, so there are 6 different ligands, each contributing a pair, 12 electrons, and they fall into the lowest lying orbitals. And so all the electrons fall into the lowest lying orbitals. In this particular diagram, we're assuming that we have a D6 complex, so we threw in 6 electrons into the next orbital to fill. But basically, this group down here, we could say we're filled. This is just us sort of making some sort of connections here. We could say that those were filled from these electrons in these donor orbitals, right? These ligand orbitals, right? So these are ligand-like. And then the metal contributes the next set of electrons, we could say, right? So these electrons, we could say, were from the metal. And everything above it, we could say, is metal-like. So if we have electronic transitions from this lower region, right, this lower region that we're kind of grouping down here, to anywhere above it, we could say that these are ligand-like going to metal-like transitions. So here's a typical transition that can occur. Okay, so we have this T1U orbital here. This is of Ungarada symmetry, right? The U here is the key part. So this came from this group over here, and it was bonding with the p orbitals. So you could say this is also sort of p-like, right, in its shape. All right, so those electrons are of a different symmetry with respect to inversion than, say, the EG orbital or this A1G, right? And so we can go in a transition like that. That would be allowed by this Laporte rule, right? Or we could go up to this A1G, right? Or we could go, those are the only 2 transitions we could have in this case that would be allowed, right? Because the T2G orbital in this particular complex is filled. But this is just for a D6 complex. There's all sorts of different electron counts and different transitions that could be possible. So here are a few examples of complexes that exhibit this ligand to metal charge transfer, and these are very common. So you see one of these is permanganate, this dark purple, dark pink, whatever color you see that. oxidizing agent, right? And it is a really dark color, and it's a D0 complex, meaning that these orbitals right in this area right here are all empty, right? And so that is that's a case where we would have a transition from maybe a T1U orbital like here. This is usually the highest occupied ligand-like orbital into this empty T2G orbital, right? That would be the case for permanganate. The other example, the next two examples here, cadmium sulfide and mercury sulfide, are both very brightly colored complexes. Cadmium, both of these have been used as paints and dyes for a long time. Cadmium yellow is still widely used in paint. And that's a transition now, it's a D10 complex, right? So that would mean that the T2G orbitals and also the EG orbitals are all full in this example, right? And so in this case, this arrow right here is impossible because it's going to a filled orbital, but the first allowed orbital transition is here to this A1G, and that one is allowed. So these would be T1U to A1G star, okay? The star here is just to help us see that that's an antibonding orbital of that set. Iron oxide, this red rust, right? That is also a charge transfer complex, and that's a D5 complex, high spin. And so in that case, we would have a single electron, you can ignore these, right? Single electron in each of those. And likewise, we'd have a single electron in these spots, right? And now we have allowed transitions potentially to T2G, to EG star, or to A1G star, right? I believe that the transition we see in this particular complex is maybe one of these spin down electrons transferring right there, okay? So again, this is very common. Most of the bright colors you see from metal salts or metal complexes are charge transfer bands, because anything else would be this very pale color. And often it's ligand to metal charge transfer. The other type of transfer we can have, though, is a metal to ligand charge transfer. And so in this case, we start with filled orbitals in some way, and we transfer up into some unfilled orbital of the opposite parity. And so it would either be from T2G to this T1U, that's the next orbital up in this very simplified diagram, right? Or maybe if we had even more electrons, maybe a D10 complex to begin with, we could imagine this transfer occurring, right? These would be two different energy bands. We may see two absorption peaks in this particular case, or more. We saw that it splits in a more complicated way typically. So some examples of this, and these are not as common, are these two complexes, not things you'll run into on the street, but these are carbonyl complexes of two different metals, tungsten and iron, with some pi acceptor ligands added to it. Okay, so these are all pi acceptor ligands, the carbonyl and phenanthroline or bipyridine. And what that does, if you recall, is it generates a new T1U. It generates new orbitals of all over the place, right? But it generates a new T2G orbital and new T1U orbitals, and they're close in energy to each other. And so it's typically a transition from something like a T2G or this EG into the low-lying T1U. These two arrows that I drew are appropriate, just depending on the electron count.